What's the setup again? You said it was like, you have this amount of multiple choices calculated, this without calculator, these FRQs with calculator, these without calculator?
Right, there's 4 sections to the exam tomorrow. You'll have 28 questions, 28 multiple guess questions without a calculator. Then you'll have 17 multiple guess questions with a calculator. Out of those 17, there's normally 2, 3 that require the calculator in order to have any chance of getting it right. The rest of them you can normally do without the calculator, but you have the calculator for those 17. Then we're going to take about a 10-minute break. Come on in. We'll take about a 10-minute break, and then we'll come back and you'll have 2 FRQs that you can use your calculator on. After that, you'll have 30 minutes for those 2 FRQs. After those 2 FRQs, after that 30 minutes is up, you'll have to put your calculator away. You have 4 more FRQs, and you have 1 hour for those 4 FRQs. During that hour, you can go back and look at FRQs 1 and 2, but you can no longer use your calculator. So that's the layout of the test. We'll start in the morning a little bit after 8. We'll probably finish up about 11:30-ish is what we normally do. It's 55 minutes and 50 minutes and then 30 minutes and then an hour, I think, are our time schedules there. Questions about how the test is graded. I'm going to grade it exactly like the exam will be graded in May, okay? There's a possibility of 108 points on the exam. The multiple guess count 1.2 points each for a total of 54 points. The 6 FRQs are 9 points each for another total of 54 points. So if you get into this range right here, 46 to 57, that equates to a 3. That will probably give you around a B on the exam. That'd be normal, okay? So 82, 83, 85, 87, 88, somewhere around in there. If you're up here in this 4 range, then that's definitely going to be in the A's, probably low to mid A's. And when you get up to here to this, that's a 97, 98 on the exam, something like that.
What if you're in the 2 area?
Okay, this area down here is probably going to go from mid 70s to low 80, something like that. And this range here is going to go from 0 to probably low 70s, 72, 70, something like that. So, you know, if somebody scores a 35, 36, they're probably going to get a 72, 73 on the test, something like that. But this is not something where you should go home tonight and cram all night long trying to get ready. I think that's an excellent way to be sure that you don't do well tomorrow. The most important thing, I think, for you is to come in tomorrow with a little bit of an arrogance about you that you're ready for it, and with a good, fresh night's sleep so that you can move forward and be able to think. The biggest thing for a lot of students is time management, and it's, gosh, and we've been used to taking 2 hours on a test, but now we're talking about 3.5 hours, and you're going to have to manage your time well. Whatever you do, don't leave a multiple choice question blank. No, even if it's just Christmas treeing it in the last 2 minutes, don't leave one blank. The worst thing that can happen is you miss it, and if you don't put anything down, you've already missed it. Yes, sir.
I just got to ask, what on earth is Christmas treeing? I keep hearing people say that. I have no idea.
You know, like
boom, boom.
ornaments and lights on the tree, they just kind of put everywhere.
Just randomly.
You
Yep.
just choose dots.
Yep. Yes. I like this one, this one, this one. Okay. Okay.
For some reason, I thought maybe like making a Christmas tree out of that.
No.
Not quite.
All right, today we're going to talk about our last new concept, and that concept is, once again, about volumes. But before we get into that, let's talk a little bit about what would you say our base formula for finding volumes is right now? We're going to be talking about 45 today.
Pi r squared dy over dx.
Pi r squared, okay? And we've got some different variations for that. But is pi a function of x squared dx, or pi a function of y squared dy? That's what we're looking for. Where did that come from?
The formula pi r squared.
Yeah, But why do we use pi r squared? I mean,
That's the way the math people, we know what enough to do it.
because what are we doing to make these shapes?
Putting them in circles.
Yeah, we're taking, what we're doing is we're taking a graph and we're rotating it around something. So that's what makes the shape. And that we can create a lot of different shapes by doing something like that. But we can't make every shape. Not every shape in the world is made by rotating something around an axis. For example, let's look at this shape that I've got right here. Where is it? There we go. Let's look at this shape down here. Can you see this?
What is that?
I don't know what it is. It's a very funny looking shape. Would you agree with that? It's a very funny looking shape. And if you, let's come down here and look at it on this end. You see that this end kind of looks like a square. But then the further back I go, each square is getting smaller and smaller and smaller until I get all the way back to the very back of it where it just comes to a point. So this is what the base of this shape looks like. So this is the base of it right here. But then when we build it up, we're taking a piece from that's the same length as it is from the x-axis up to 1, and we're making a square out of it. And then as we get smaller and smaller, we're making smaller squares. So we wind up with some funny looking shape that looks like that. Okay? Now, does it have to be squares? No. We could make it so that it looks something like this. Notice we didn't change the base, but now look at what the shape looks like. Now, if we come down here and look at this end again, now we've got triangles. We've got a triangular shape. Or we could make it a semicircle shape. So how does that look? See, now it's a semicircle, but the base of it is this. And notice what's happening when we get all the way back down to the point here at pi over 2. It's getting to nothingness, okay? Yes, ma'am.
I think I have an epiphany.
You've got epiphany. All right. So give us an epiphany.
Plugging our equation in for R for each of these areas.
Something like that. Yes, very much like that. So I want us to take this now and let's talk about this for a few minutes and let's think about what this means. And to do that, I want us to go back to how we found the areas to begin with of with pi r squared. Do you remember we were kind of making discs? Because we would kind of slice through it and say, okay, so that's a disc, so we find the area of it times how wide the disc is, and we just keep adding those together. If you'll go back and remember, let me see if I can pull it up here. If we go back to, where is it, the disc method right there. Okay, something like this, and we started off with something that maybe we only had about 3 discs in there, okay? So see, we're taking this is where we started at, and we would take this largest disc out here and rotate it around, and we'd say, okay, if we find the volume of it, pi r squared times the radius from 2 to 3, which is 1, times the height of it, I mean. These were all approximations, right? But they were not good approximations because you see that they overlap or they don't cover all of the areas. So what did we start doing to make it better? We made smaller rectangles, put more rectangles in there, and then the more rectangles we put in there, the better approximation we get for what the actual area is, and the more smooth the curve gets. Well, we're going to do something very similar to that with this here. We're going to start off, let's start this process off here with less rectangles. Let's start off with just 3. Okay? Now, what does that look like?
I don't know, but it's cute.
Okay? So now, and let's go back to the figure that we had to begin with. We have got squares. How would you find, so now if we look at this figure, do you see that we just got 3 boxes there? So how would you find the area, if we're calling this box 1, and this box 2, and this box 3, how would you find the volume of box 1?
Somebody found the volume of, rectangle.
Okay, and what's that formula?
Oh, man.
Anybody remember? It's volume, so you got to multiply 3 things. Length times width times height. So now, since we know that, what do we know about these two? Stop floating around so I can draw on you. What do we know about these two dimensions here and here, since it's a square? They're equal, yes. So if whatever this is, whatever this distance here is, this distance up here is the same thing. So they're both the same thing. And then what about the height of it? That is, in this case, is 0.5 or about 0.5. Would you agree with that? Okay. So we just need, really, we need to know what these two dimensions here are. How do we find out what those two dimensions are? How tall is this box? That's going to be this dimension here. How do we find that dimension right there? Any ideas?
Plug in.
Whatever that number is, into what? Into the function, which I think this is cosine, yes. So then, for this, if we wanted to work this one out, it would be the cosine of whatever that number is there. I'm going to call it A squared times whatever this distance is right here, right? The 0.5. Y'all agree with that? And then, how do we find 2? Same thing. So it's whatever this number is here. We'll call that number B. We'll call that number C. So then it would be the cosine of that number squared times 0.5. And it would be the cosine of that number squared times 0.5. And if we had more rectangles, what would we do? We just keep doing that. Okay, so if we had, instead of 3 regions in here, if we had 30, we would just do that for all 30 of them. And do y'all see that there's a similarity then between that and what we were doing before? What's different about this, what we're doing right now, and what we were doing when we were rotating it around? We multiplied the 0.5, but now as we put more rectangles in here, what's going to happen with the 0.5? It's going to get smaller and smaller. And when it gets smaller and smaller, if you were to go back to when we started before, we had a number in there. What did we replace that number with as we got smaller and smaller? Do y'all remember? dx. So we took care of this 0.5 out here simply by changing this into integrating and dx and using whatever our function was. Our function in this case was cosine squared. So if we were to integrate from 0 to pi over 2 cosine x quantity squared dx, we would be finding the volume of this shape that we've got down here. Okay?
So what are we finding it around the whole, like a circle?
Very good question. She's saying, that's right. We didn't put a pi in front of this, okay? We're not rotating this around the x-axis. We're just finding that area because we know that the cross sections, we know that if we cut through this shape at any place, the area that we find is going to be a square, as evidenced by looking at that there, okay? So this is this cross section is a square. So this formula in here becomes cosine of x squared. What if, however, what if we don't have a square? Huh? Come on, erase for me. Erase. This is, I want it there. Oh, well. This is about the best I can do here. What if, instead of squares, what if we've got triangles? What if when I look at them from the end, I see an isosceles right triangle? That's right. Now, how does that change my formula in here? That's going to change it. We're still integrating dx. We're still integrating 0 to pi over 2. But now our formula in here changes to 1/2. What's the base of the triangle? It's whatever this distance is from right here to right here, which is cosine of x. What's the height of this triangle? This distance here. Remember, I said it was an isosceles right triangle. What does that mean? They're the same. So it's just that same thing again. So it's the cosine of x squared. And that's what we're integrating. Is that hard? Okay, this is called finding the volumes of known cross-sections. Okay, that's what we're talking about here, is finding the volumes if we know what the cross-sectional area is. For example, if we were to look at, these are all examples of things that we can find the volume of because we can find the volume of a cross-section of them, okay? If we were to take, y'all know what this is up here? Bread. If we take bread and slice through it, every shape is basically the same shape. Would you agree? Now, these end pieces out here are a little bit smaller than the middle pieces normally, right? Would you agree with that? But they're basically the same shape. And you can find the volume of the whole loaf of bread by finding the volume of each piece and putting them all together. Because when you slice through it, it has a known cross-section. We could create a formula. We could come up with a formula to find that area, to find that volume. All we need to figure out is what's the area of the face of it. That's what we're asked to do. Same thing with this pear down here. Notice that the pear's cut in half, and then if we slice through the pear, we get these little circular shapes here. As long as we can come up with a formula for that circular shape, then we can find the volume of this figure. Look at this thing up here in the top. We can find the volume of that funny looking thing right here, because look at what shape would you say the cross sections are? They're squares. What's the area of a square? No, length times width. Pi r squared is a circle. So length times width. As long as we can come up with a formula for how high this thing is or how wide this thing is, then we can integrate it from here to here and we can find the area of it. So we've changed, when we've got known cross sections, our formula changes a little bit. We don't have a pi in front. Okay? It's just going to be an integral dx, and this is going to be an area formula that you use there, okay? It might be the area of a triangle. It might be the area of a square. It might be the area of a semicircle.
But it's only the face.
That's right. It's the area of
Like the area of a cube.
no, because that's volume. Cube would have volume or surface area. It's going to be the area of a face is what it's going to be. The area of one of the faces is what you're going to be looking to find. So let's look at this example right here. All right? I have an equation right here. This red equation is y equals 9 square root of x. All right? Y equals the square root of x. Now, if we're going to find the area, and these squares are going to be drawn on here like this. Let me give you a picture of what they look like. We've got a square right here, and then whatever that distance is there, it comes out from the board that same distance, so that this little square that I'm looking at right here is actually way back here, and I'm standing to the left of the board. So the picture that you're looking at is as if I'm looking at it from here outward, okay? I'm looking this way. This is what I would see. There's a huge square down here at the end that is that long, and that's what 3 long that way is 3 out this way. So now this is the direction that our squares are going to be going, okay? What is our integral that we're going to be integrating there? Can you tell me? Do you think we're integrating with respect to x or with respect to y? X. Okay. Well, it could be either one. We can't say x because of this thing up here. Okay. How do we know that it's x? Because look at where these cross sections lie. Look at where these green lines are. They're intersecting the x-axis. So we're going to be cutting it this way, and then we're going to be adding up from this point down here all the way to this point. So all of those are x's. So we're integrating with respect to x, so it's dx. So what are our limits of integration then? 0 to 9. Very good. And now, the shape that we're looking for is a square. So then what are we integrating? Square root of x, quantity squared. Why is it square root of x? Because we're told that this red curve is y equals the square root of x. So that means the distance from the x-axis at any point up to the curve is the square root of x. So if we integrate from 0 to 9, the square root of x squared, whatever that works out to be, that would be the volume of this model that we've made in this picture up here of these squares. And it's going to be getting smaller and smaller and smaller when you get back closer and closer to 0.
Is there pi in front of the whole thing?
There's not a pi. Why is there not a pi?
Is it squared?
Not because we're not rotating. Okay? You're only going to put a pi out here. Well, I'm not going to say on. If you're rotating it, you have to have a pi out in front. We're not rotating this about the x-axis. So when you get to this problem tomorrow on the test, how are you going to know to use this? Okay? How are you going to know to use this? It's going to say cross section. When you see volume cross sections, you're going to know cross sections means I'm not going to have a pi out in front. Okay? That means I'm going to be looking for words in the problem that say area is the cross section is this, and I'm going to build my problem from there. Okay?
Does it always, does it have to give you the shape, or you assume to know that it's...
No, we're going to always be told what the shape is. We would always be told exactly, because we're going to work through this problem here a bunch of times with different shapes here. All right? What about this? This is the same, similar problem. Y equals the square root of x is what our function is. Find the volumes of known cross sections with the cross sections in the shape of a semicircle. And I need to say this here. Perpendicular to the x-axis. Okay? Perpendicular to the x-axis. So if we're drawing our semicircles on here, where are we drawing our semicircles at? Can anybody tell me? Yes, we're going to start at this point here, and we've got a semicircle going all the way down here. And at each one of them, it's going to look like this. So when we get back down here to the end, it's coming to a point at the very end back down here. So if you think of it, it kind of looks like a huge, if I'm standing out here and looking in, it looks like a huge open building, maybe. Huge circular top. Doesn't have any walls. The top just comes all the way down to the ground. And then as I walk back in here, the building keeps getting smaller and smaller and going to that point back there, okay? So how are we going to find the volume of this thing? Integrating. Since it's perpendicular to the x-axis, it's going to be 0 to 9, and it's going to be dx. If you don't know anything more than that, that probably gets you a point of the 3 that you could get out of this, okay? So 0 to 9 of dx, okay? We know it's the shape of a semicircle. So that tells me I need to find out what's the area of a semicircle. Can anybody tell me?
1/2 pi r squared.
Yep. 1/2 pi r squared. Okay? So I'm going to be integrating 1/2 pi r squared. What's my radius? What's the radius of this semicircle? Square root of x? No, it's not the square root of x.
The square root of x over 2?
Square root of x. Ooh, are you asking or telling? He said no, so he wasn't telling me if you're sure. Okay, where's square root of x is from right here at 4 all the way up to 2. Would you say that's the radius of the semicircle? That's the what? That's the diameter. So it would be over 2. So it would be over 2, okay? Because the square root of x is this entire distance from the x-axis up there. And we only need half of that for our radius. So it is the square root of x over 2. But we have to square that, okay? And now you could integrate that. I'm confident you could do the integration there, okay? How do you feel about that? Okay, let's do a few more. Isosceles right triangles perpendicular to the x-axis with one leg in the xy plane. Okay? You can get lost in all the words there, okay? But let's see. Tell me what you can read from that and know for sure you need. Isosceles right triangle perpendicular to the x-axis. What does that tell you already that you can write down towards your answer here? dx. Now we can write out an integral sign. If you wrote in dx, you ought to be able to write down something else. 0 to 9. Very good. Okay. We know this is still y equals the square root of x. Okay. So now we need to find the area of something. What area formula do we need to know? Isosceles right triangle. Okay. So what's the area of an isosceles right triangle? Anybody remember? 1/2 base times height. Okay. Well, that's for all triangles, yes. Yeah, that's the area of all triangles. But how do we find 1/2 base times height? Well, no, the base is 9 right here. But the base is not 9 down here. The base is square root of 5 right there. The base is the square root of 4 right there. Yes. So the base here is the square root of x. Now, dx is taking care of another dimension here. So we've got to know what the height of this triangle is also. What's the height of this triangle? With one leg in the xy plane. So that means when I'm looking at this, this is one leg, and then there's another leg starting right here at 8 coming out that's the same length of that. And then it goes back into the board at a right angle, at an angle. So I've got, it's a 4, so the base is the square root of x, and the height is the square root of x. Okay? With an isosceles right triangle, both of those dimensions would be the same.
So it would just be x.
Right, so we're integrating 1/2 x from 0 to 9.
So then the dx isn't the height anymore?
No, the dx, think of the dx as the width of this rectangle. Remember, the basis of this is we're making a rectangular cut through there. dx is this distance right here. dx is giving you the third dimension because you've got to have a length and a width and a height. So I don't know which. That's right. This is an area formula right here. This is the third dimension. The dx is giving you that third dimension. So it's 1/2 square root of x squared, or 1/2 x that we would integrate from 0 to 9. Not necessarily. Well, this would be square root of x squared like that, because both of those dimensions were the square root of x. Okay?
What did the 1/2 the square root of x times the square root of x all squared?
Because all we need is just the area of this triangle. The area of this triangle, right here, the area of this triangle is 3 times 3, which is 9 divided by 2. The area of this front triangle that we'd be looking at is 4.5. Correct, yes. Only if it's, there's nothing in this formula here. This is always just the area. Most of the time the area is going to have, well, all the time, the area is going to have 2 dimensions. So it's very likely that something will be squared in there. But you will seldom have squared like we did before, unless squared was in this first function up here. All right, let's look at this again. What's different? Oh, perpendicular to the y-axis. So Kevin said that means dy. Now we're integrating from 0 to 3. Does everybody see how she's figuring that out? All right. Well, this red curve was y equals the square root of x. So that means x equals y squared. But now, isosceles right triangles perpendicular to the y-axis with one leg in the xy plane. Where is our leg at? All right, here's my question. Is that what y'all see as a leg now? Okay. Okay. We're looking at from there to there, and then it's coming out here. So now you'd have to get down here on the floor, and I'm looking at it from this direction. So I've got a triangular shaped house right here. You know, it's 9 this way, it's 9. You know, when I'm looking here, I'm seeing a triangular shaped house. Let me see if I can draw this in 3 dimensions here. I've got this and this and this. That's what I'm looking at. And then as I look back in there, along the lines, I've got they keep getting smaller and smaller all the way back. Ooh, that doesn't have to stand over here maybe to see it.
I can kind of see it.
But I've got a big triangle out here. Every time you go in, the walls are closing in on you, okay?
When you're going it this way, it's like a base of the triangle, and this is the side coming out. This would be, I guess, the side.
Yes, this is the base. The base of it's right here at 0 to 9. That's what this is right here, 0 to 9. Then this is coming out of the board, so that's going straight up. It's the same distance, and then we just got a roof on there from that side to there. So we've got a huge triangle opening, and then every time we go in a little closer and closer, it's getting smaller and smaller, back to a point. Those of you that have taken art, don't you have a vanishing point? Do y'all know anything about that? So think of it like that. It's kind of going to a vanishing point at the back of it there. Yes, yeah, that's right. The roof's just going to come down to the ground, and it's just going to keep getting smaller and smaller. Okay, so how do we find that? It's still an isosceles right triangle, so it's still 1/2 base times height. Since it's isosceles, we know it's going to be, the base and the height are going to be the same thing. But what are they? Y squared. 1/2 y squared squared. That's what Miss Sarabeth says, and she's wrong. Where is the distance?
One of them's not, right?
Well, but now wait a minute. It's isosceles right triangle. So that means this leg and the leg coming out the same length. But now let's just look at what we said right here. When y is 0, right here at this point, how long is a triangle? 9. That's not what we're going to get right there, is it? If we put 0 into that y squared. So this is not, y squared is not the right formula. Y squared does not describe how long this segment is from here to here. Who can tell me what tells me how long that segment is? 9 minus y squared, Very good. It's 9 minus y squared. This is how long, this distance right here at any given time is 9 minus y squared. Okay? Because when y is 0, then this distance is 9 minus y squared. When y is 1, then this distance right here is 1 squared, or 1. This distance right here, from here to there, is 9 minus 1, 8. When we get up here to the top, this distance, 3 squared, is 9. The distance right here in the shaded region is 9 minus 9, or 0. So that would be my formula. 1/2 9 minus y squared. Do y'all see any similarities with 9 minus y squared in anything we've done before? Top minus bottom, far minus close, anything like that. It just keeps showing back up, okay? So think of it, it's this distance from here all the way to there is 9 minus y squared, quantity squared. How did we know it needed to be dy? We're perpendicular to the y-axis. If it's perpendicular to the y-axis, you're going to have 0, 3. You're going to have 9 minus y squared on there. Any questions about this so far? Isosceles, right triangles, perpendicular. We've already done that. Why did I do that? Why did I want to do that so many times, you reckon? Oh, well, we've already done that. Okay, now. Okay, we're not going to do that. Y'all don't have that slide? So, how would you summarize, what's the formula for the volumes of a solid with a known cross-section? How would you summarize this?
Integrate from A to B.
Uh-huh.
Multiply by formula by
Area of the cross-section. It's not going to be squared. It's just whatever the area of the cross-section is. Now, I will tell you, most of the time, it's going to wind up with something squared in there. But it's whatever is built into the area formula. If I said they're going to be rectangles that are 5 feet tall and whatever that wide, then it wouldn't have a square. It'd have 5 times whatever this was. But every time, it's whatever your area of the cross-section is. Yes, sir?
So in other words, what we're doing with this is we just need to, we use the, what am I trying to say? Sorry, bring it back, like different. We use the area of, like, the shape that says the cross-section, then we use the graph to fill in the numbers, to like, switch out the variables like base and height for actual numbers.
Mm-hmm.
See on the graph.
Yeah, I think you've summed it up very well, sir.
Okay, I can do that.
Okay? So let's look at maybe a couple of other examples. That's just out of your book, said the same thing. I'm not going to bother you with that. Look at this figure here. This is something very similar to what you might see on a problem to be, okay? Very easy to get bogged down in, oh my goodness, what does all of this mean? Don't get bogged down in it. Look for key things that you can figure out here, okay? I look at this, cross-sections perpendicular to the x-axis. What does that tell me? dx. We know we're integrating. We know we're integrating with respect to x. Okay. Equilateral triangle kind of clues us to 1/2 base times height there, okay? Looking at the figure, what do you think is our limits of integration? -1 to 1 here? That's a y, isn't it? 0 to 2 is where we're going to be integrating, okay? So we're integrating 0 to 2. All right, now, equilateral triangles is worth starring, okay? Because there's a special formula we can use to find the area of equilateral triangles that's easier, or that's much easier to work with than base times height. Because base and height have to meet at right angles. Well, if it's an equilateral triangle, that's right, there's not a 90-degree angle in there. So you'd have to go in there and recreate it. So for an equilateral triangle, We're just saying, poof, here it is, okay? Poof, there's the formula you need to know. Square root of 3/4, square root of 3 over 4 times s squared. Yes, side, however long a side is, okay? So that's what you need to know for an equilateral triangle. The square root of 3 over 4 times a side squared. Now, how long is a side?
One.
Is that just the function?
Maybe that's.
Okay. Well, it's 2 right here, Wesley. It's 0 down here, so it's changing. Mary Martin said, is it just the functions? What do you think we need to do with the functions? Subtract them? Tell me what you would do then. Here are the 2 functions up here. What do you think we ought to do? All right. Where are these functions at on this graph that we're looking at down here? Can you tell me? This is, that's right. This is my f function. This is my g function. I'm looking for how long it is from one to the other. So how can I figure that out? Top minus bottom. Top minus bottom. That comes up all the time. Which one's top, F or G? F. How do you know F is on the top?
Higher up on the y-axis.
Higher up on the y-axis. That's a logical way. So we've got top, 1 minus x over 2, minus bottom, negative 1, minus x over 2. Notice I distributed that through there, okay? I distributed the minus through, squared. So yes, that'll become plus 1 in there. So top minus bottom, quantity squared. There's one of these on the exam tomorrow. It's the third part of one of your FRQs, just like that FRQ that we've been putting off for 2 weeks. It's part C on an FRQ. This is 3 points worth right here. Being able to say it's dx, and 0 to 2 is probably 1 point. Being able to get a formula in here for the area is 1 point, and getting the answer is going to be 1 point. It's a calculator activity. After you do a few of them, they really start falling into place there. All right? We've already done that one, haven't we? Yep. We just did the semicircles there, okay? We did isosceles triangles with the last one that we just did there. Let's look at this problem. Rectangles with height 3 times the width. Okay? So now, since I didn't state it here, I'm going to clarify. The rectangles are right here. So is it dx or dy? Dx. So we're dx. So we're integrating 0 to 9. We know this is y equals the square root of x. Now we're doing rectangles. How do we find the area? How do you find the area of a rectangle? Length times width. Length times width is going to be area of a rectangle. Yeah. So length times width. It says the height, or height times width, since I said height there, okay? If we do height times width, the height is 3 times the width. Well, how wide is it? Yeah, but how wide are our rectangles? Can you tell me?
1.
No, I mean, okay, we've got to do all of these rectangles, okay? So let's be sure we're looking at the same thing. When I'm seeing my rectangles here, this is the base of my rectangle right here, and then it goes up. So now when I'm standing here looking at this building, I see a huge building. It's way tall. And then as I walk in the building, it just keeps getting closer and closer to me here. I'm getting claustrophobic because the ceiling's coming down too. So it's just going to be large rectangles that keep getting smaller and smaller until I get back down here to the corner and I can't even get in the corner because they're getting smaller and smaller. So the width is this distance right here. How wide is this thing?
9.
But I need a formula. because it's 9 right here, but when I get back here at 8, what is it?
So,
It's not 9 right there. How wide is it?
So
3.
minus square root x.
It's 3 there.
so it's, the width is the square root of x.
So the width is the square root of x. Okay? Because when x is 9, its width is 3. When x is 4, its width is 2. When x is 1, its width is 1. The width is the square root of x. Now what's the height?
That's that's y squared.
3. So what does it say? 3 times the width. What's the width? 3 times the square root of x. So I'm integrating 3 times x. I'm integrating 3x from 0 to 9. Feeling any better? This is a good place to be with this. Good place to be. We've already talked about that. All right. These are not always, these get to be a little bit more tricky when we look at something like this. This is a solid whose bottom is a circle. And every cross section perpendicular to the x-axis is a square. Okay? Yes, that sounds horrible. But let's look at what we've got. What can we do? Dx or y? Dx. Where are we integrating from and to?
I guess you,
It's a circle. It's x squared plus y squared less than or equal to 1.
so it's going to be 1 to something.
1 to negative 1. Because think of it, it's a circle. There's the center of it. If that's 1, then that's negative 1 back there. So we're integrating negative 1 to 1. Dx. Okay? We know that the areas are squares. Right? So what do we need then? Base times height. And since it's a square, they're the same. So we need something in here. We need some kind of formula, if you will, in here that says something squared. And this thing in here just needs to have x's in it, right?
So,
How can we do that?
It would be the square root of 1 minus.
If we look at this thing right here, that's the only function-looking thing we've got on the board, right? So we could say that means y squared is 1 minus x squared. So that means y equals plus or minus the square root of 1 minus x squared.
But it kind of goes away once you square the plus or minus.
Yeah, but now, since I get a plus or minus there, okay, let's go to this picture right here. How long is that thing right there? How far is it from one side all the way across there? It's 2 right there, but see, I'm looking at, it's getting slanted each time there, so it's getting smaller. It's the maximum right there at 2, but it's getting smaller as I come out this direction. It's getting smaller as I come out there. What is this distance right here at any given point? How far is it across there? Any ideas?
square root of x.
All right, well let's see. Let's see. This is x, this is y.
It goes from negative 1 to 1. Is that why it's negative? Like it has to be negative, or like the area below.
Right. I want to take this pink area and draw it in one dimension for you here, okay? So this is what that pink area looks like in one dimension. That's x, that's y. Now I've got a circle right here. If I want to solve that circle, though, so that what is this top part of the circle? It's a semicircle, and its equation is 1 minus x. Let's rewrite it. Its equation is y equals the square root of 1 minus x squared. That's this top part. What's the equation of this bottom part down here? It's the negative one of those. So when I'm looking for the distance from here to here, how do I figure that out? Same things we've been doing all this time. Top minus bottom. It's going to be the square root of 1 minus x squared minus the negative square root of 1 minus x squared. That's this distance. Is that what we need to be integrating? It's the same thing as 2 times that. But this is just one dimension. Don't we need a second dimension? Don't we need to know how tall it is? How tall? It's this whole thing squared. Okay? Now, I think some of you had gone steps further than me, like you had said, okay, so this is just 2 the square root of 1 minus x squared. Yes, it's fine to do that because it's going to be the same thing. But this that I've got written underneath the green line right here could be simplified to that. You can keep simplifying it as 4 parentheses 1 minus x squared before you actually integrate it. But do you see that with this over and over, top minus bottom? Everywhere you look, you see top minus bottom, top minus bottom. It's just going to keep coming up over and over and over, okay? All right. These are some of the most challenging things to deal with conceptually. You've got a few of these that you can work on as practice. I think it's listed as due tonight. It sure would be nice if you got it done tonight. If you don't, that's fine too. But there will be one of those on the exam tomorrow.